What we perceive as the loudness of a sound, that's related to the intensity of the sound. The larger the intensity of the sound wave, the louder the sound is going to hear to our ears. So there's a couple of different ways we can define intensity of a sound wave. But first, let's talk about the intensity here in this way. So the intensity of a sound wave is related to the pressure variation of the sound wave and the density through which the material is moving and the speed of that sound wave. Okay, so the intensity of a sound wave is equal to the square of the pressure difference of the sound wave divided by 2 times the density of the material through which the sound is moving times the speed at which that sound wave is moving. Here, for example, we have a little bird and it's creating a sound, okay? This is the graph of the pressure of that sound wave produced by the bird as a function of distance away from it. That's what we were plotting in the previous mini lecture. We were plotting the pressure of the sound wave as a function of distance. Okay, so it makes a little squawk. The amplitude of that pressure variation along the wave is small, but it makes a big squawk. It's making a louder sound. And the amplitude then of the pressure variation from that sound wave that it created is greater. And so it's this pressure variation in our longitudinal sound wave that is creating the intensity or the loudness that we perceive of the sound. A more formal definition for intensity is right here, which works both for sound waves and also for light waves, that the intensity is given as the rate at which energy flows through a surface divided by the surface area through which it's flowing. Okay, so the rate at which energy flows, that's an energy per time. That's a power, okay? And so that power of the source has units of watts. And then we have the rate at which energy flows through a surface, that's the power, divided by the surface area through which that energy is flowing. That gives you the intensity. Okay, so let's think about that over here. So here we have a point source of sound waves, just like that speaker that we saw earlier. Those sound waves are going to propagate away from that source in a spherical shell, okay? And so as those sound waves propagate out, we can find the intensity of that wave at some distance away from the source. And the intensity is the power, the rate at which energy flows. So that power of the source is always constant no matter where you are, no matter how far you are away from the source. And then you divide that power by the surface area through which that energy must flow, okay? And then that surface area, though, is going to change the further out you get away from the source. So the surface area of a sphere, that's the surface area that we're talking about, this concentric sphere centered on the source of the sound, that surface area is 4 pi r squared, or 4 times the radius squared, where that r is the distance that you are away from the source. So the farther you are away from a source of sound, the less intense that sound is. You know that, you've experienced that in your life. The closer you are to a speaker, the more intense that sound is, the louder it will be. The farther you are away from the speaker, the less intense that sound will be, the less loud that sound will be. And this is an example of what we call an inverse square law. The intensity is inversely proportional to your distance squared away from the source. So what that means is that, well, actually it's shown right here. If we double the distance that we are away from the source, we actually reduce the intensity by a factor of 4, okay? Because if we're doubling that distance, so instead of r, we're at a distance 2r away from the source, intensity is related to 1 over the distance from the source squared. So 1 over 2 squared is 1/4. So by doubling the distance, you reduce the intensity of the sound by a factor of 4. Triple the distance, you reduce the intensity of sound by a factor of 9. The units of intensity are watts per meter squared, okay? We have a power, which has units of watts, and then we're dividing it by an area. Area always has units of length squared. So we have a watt divided by a meter squared for the units on intensity. Now, there's another way we can talk about intensity, and that's by thinking about what we call the sound intensity level given in units that we call decibels. Now, our human ears perceive intensity on a logarithmic scale. Logarithmic scales are scales that are proportional to powers of 10. A useful measure for intensity then is given by what we call the decibel. And so we're going to represent our sound intensity level in units of decibels by this Greek letter beta here, this fancy B. So our sound intensity level in units of decibels equals 10 times the logarithm of the intensity of the sound divided by this quantity that we call I sub 0 or I sub naught. This value, I sub naught, is the softest sound that most people can hear. And that softest sound is 1 times 10 to the minus 12 watts per meter squared. So our sound intensity level in units of decibels is calibrated to our human ears, where we've got this softest sound that we can hear, and everything is relative to that, essentially to power of 10. And that's what this sound intensity level in units of decibels is telling us. So if you multiply a given intensity by a power of 10, it adds 10 decibels to the intensity level. So for example, this is a chart that I just took from your textbook of the intensity of the sound, which is given in watts per meter squared, and then the sound intensity level, which is given in decibels. So remember we said that the threshold for human hearing is 1 times 10 to the minus 12 watts per meter squared intensity. That's the softest sound most of us can hear. So on the sound intensity level, that unit in decibels for the sound intensity level is 0. So we're doing everything relative to what our ears can hear. Now, when we increase the intensity by a power of 10, we go up to an intensity of 1 times 10 to the minus 11 watts per meter squared. That's like the rustling of leaves outside right now. That increases our sound intensity level by 10. We go up by 10 decibels. Okay, now if we go up to a sound intensity level that's a factor of 10 larger, 1 times 10 to the minus 10 watts per meter squared, that gives us another plus 10 for the sound intensity level in decibels. So now we're at 20 decibels on our sound intensity level, but we're at an intensity in units of watts per meter squared of 1 times 10 to the minus 10. So when you increase by a factor of 10 the intensity level, you add 10 to the sound intensity level in decibels. Our threshold for human ears, when we get too high of an intensity, it's like when our ears start to have damage caused to them by the intensity of the sound. That intensity is 1 watt per meter squared. And that's the sound intensity of a rock concert, let's say. If you get really close to the speakers, you can cause damage to your ears if you're not careful. And that in the sound intensity level in units of decibels is 120 decibels. We can actually burst our eardrums if we get up to a sound intensity level of 160 decibels. And now we're going to work through a problem where we think about the intensity variation of sound from a point source. And we're also going to show how you can use the equation for the sound intensity level in decibels. Let's work through a problem where we think about the intensity variations of a point source of sound. So let's imagine a sound system speaker here. That's my speaker, as a point source emitter of sound. So it's going to emit these sound waves away from itself in these concentric spheres. Okay, and each one of these spheres we call a wave front, and that represents a compression of air. This small sound source emits sound waves with a power output of 80 watts. Okay, we are going to do a couple of different things. The first thing that we're going to do, part A, is find the intensity of this sound 3 meters from the source. Intensity at 3 meters, okay? We know that the intensity of the sound is equal to the power of the source divided by the area. And in this case, the area is the surface area of a sphere. These sound waves are leaving from the source, and they're going out in these concentric spherical shells. So this area here is the surface area of a sphere, which is 4 pi r squared. It's also on your equation sheet. Okay, so this is P over 4 pi r squared. We know P. We're trying to solve intensity, and we're already given the distance r. R is our distance away from the source. So we can just go ahead and plug everything in here. So this is just going to be 80 watts divided by 4 pi times 3 meters squared. So the intensity of sound at 3 meters from our source, if the power output of our source was 80 watts, is equal to 0.707 watts per meter squared. We've got the watts here, we've got the meters squared, so those are our units for intensity, okay? And then for part B, at what distance, so I'm going to call that distance R2 equals question mark, at what distance would the intensity, I2, be 1/4 as much as it was at 3 meters? So at what distance would the intensity be 1/4 that of I1? Question mark, okay? So in order to find that, well, let's see. We can again use our equation for intensity. This time I'm going to say that I2, our new intensity, equals power of our source divided by 4 pi, we got R2 squared here, okay? So I'm going to solve this for R2. That's the distance I need to be away from my source so that we have 1/4 the intensity of what we found for part A when we were at 3 meters away from the source. So if I solve this for R, what I can do is I can multiply both sides by R2 squared. That cancels that out over here. Multiply this side by R2 squared, okay? And then what I'll have to do is divide both sides by I2. Oh, divide by I2, okay? So then R2 is going to equal the square root of the power divided by 4 pi times the intensity at our new distance away from the source. And at this new distance away from the source, our intensity is going to be 1/4 of what it was up here. And so I'm going to write this actually as the square root of P divided by 4 pi times 1/4 I1, because the intensity at this new distance that we're trying to calculate is going to be 1/4 that of the intensity that we had at 3 meters away from the source. So that's why I replaced I2 with 1/4 I1. And then you can see that this 4 times 1/4, they're going to cancel here and here. So then my new distance is going to be the square root of P, the power, divided by pi times our original intensity. So this is 80 watts divided by pi times 0.707 watts per meter squared, and I have to take the square root of that. So my new distance is going to be 6 meters. So I have to be 6 meters away from my source to have an intensity 1/4 that of the intensity at a distance of 3 meters away from the source. Okay, so this is an example of an inverse square law. So we see that if I double the distance, I reduce my intensity by a factor of 4, okay? Because remember, the intensity is proportional to 1 over the distance away from the source squared. So if my distance is twice what it was originally, if my distance is 1 over 2r this time, and I have to square it, that means that my intensity is now going to be 1 over 4r squared, or 1/4 what it was originally. Now for part C, we're going to find The distance away from the source at which the sound level is 40 decibels. So we're looking for, I'm going to call this R3, at which we achieve a sound level of 40 decibels. Okay, so how are we going to figure this out? Well, first of all, just to point out that 40 decibels is generally the average kind of ambient noise that you have around your house. So that's about 40 decibels, so not too terribly loud. Okay, so we have our equation for the intensity level in decibels. In that equation for our intensity level in decibels, which I'll write like this, beta is our intensity level in decibels, that's equal to 10 log of base 10 of the intensity divided by this quantity that we call intensity sub naught. This intensity right here is the softest sound that a human can hear. And the intensity for the softest sound that an average human can hear is 1 times 10 to the minus 12 watts per meter squared. Okay, so that has an actual quantity we can give it. So in order to get the distance at which we have a sound intensity level of 40 decibels, the first thing we want to do is convert from decibels to intensity in watts per meter squared. And this equation lets us do that. Okay, so we've got our intensity level in decibels. We've got 40 decibels equals 10 log 10 of I over I naught. Okay, now if we divide both sides of this equation by 10, then we have that 4 is equal to log base 10 of the intensity over our kind of threshold intensity, I naught. Now the thing that we're trying to solve for is this intensity right here, but it's inside here, it's inside our argument for the log. So how do we get rid of this log base 10 right here? Well, there's a relationship that you probably learned at some point that 10 raised to the power of log of some number gives you back that number n again. To get rid of this logarithm then, now what I'm going to do is take 10 to the power of 4, and that equals 10 to the power of log I over I naught. So when I do that, the left-hand side of my equation becomes 10 to the 4, and the right-hand side of my equation, as we said, that 10 raised to the power of log of a number, if this is log base 10, you get back that number in the argument again, okay? So if I do 10 to the power of log base 10 I over I naught, I get back this argument inside my logarithm. And so this is equal to I over I naught, okay? So then I have an expression for this new intensity. So the intensity of our sound at 40 decibels is equal to I naught times 10 to the power of 4. Now I naught is the softest sound that a human can hear. That's 1 times 10 to the minus 12 watts per meter squared, and I multiply it by 10 to the 4. So this tells me that 40 decibels is the same thing as 1 times 10 to the minus 8 watts per meter squared. Okay, so 40 decibels is equal to 1 times 10 to the minus 8 watts per meter squared. Well, I put a box around it. We're not quite done yet. I've put a sub 3 here to help us distinguish it from the other intensities that we talked about in the previous parts of the problem. Now, we also saw earlier that at 3 meters away from the source, we had an intensity of 0.707 watts per meter squared. I'm going to call that I1. Now, we can set up a ratio where we say that I1 over I3 equals, because we already know what I1 and I3 are, we can set up this ratio that says that I1 over I3 equals the power of the source divided by 4 pi R1 squared, because we saw that the intensity of the sound is equal to the power divided by 4 pi r squared. Okay, and then we're going to divide this by the power of the source, which doesn't change, divided by 4 pi r3 squared. Okay, so we've got the powers canceling on top and bottom because those are the same. We've got the 4 pi canceling on top and the bottom. Then we have the I1 over I3 equals 1 over r1 squared divided by 1 over r3 squared. So here we're dividing by a fraction, same thing as multiplying by the reciprocal. So this is equal to 1 over r1 squared times r3 squared over 1. Okay, so I now have this expression that says that the intensity I1 over I3 equals r3 squared over r1 squared. Okay, and I'm trying to solve it for this distance that I called R3, which is the distance at which we achieve a sound intensity level of 40 decibels. So earlier we already found what the intensity of 40 decibels is in watts per meter squared. We found earlier that at a distance of 3 meters from the source, the intensity was 0.707 watts per meter squared. So we have all these pieces of information. So if I solve this equation for R3 is going to equal the square root of R1 squared times I1 over I3. Okay, and then for this problem, that's going to equal 2.52 times 10 to the 4 meters. That's pretty far away. Okay, so you have to be, that's 25,200 meters away from the source in order for you to eventually get a sound intensity level of 40 decibels, which is about the sound intensity level that you have at home.